Hi everyone. Since we couldn't go through lab 4 during the demo because of those MATLAB issues, I'm just going to make a little video on how to do part C because I think that's the more complicated part of this lab. So I have lab 4 part C pulled up on this document here, and then I opened up MATLAB for systems lab. So I'm just going to kind of walk through system A with you guys. So you want to make your input signal 80 and then system A, and it should be in pascals, and so you'll click run system. And so you have your input here and your output here. So first it asks you to find a max, and that is just the maximum amplitude of the output. So you see amplitude is on the y-axis here and frequency on the x. So to find the maximum amplitude, I'm just going to use this little tracing tool and just click anywhere on this top line because it's all the same line, so it's going to be the same amplitude. Yeah, and you can just click around a little bit. Looks like these are all 1.995, so I don't think it'll get any higher than that. So you'll come over here, put 1.995 under your max amplitude. And then it asks for a half, which is just half of this amplitude value you just obtained. So half of 1.995, you should get 0.9975. And then it asks you to look for F cut, which is the cutoff frequency of the system. So to find that, we're going to use this amplitude, this a half value, and we're going to find the frequency where this amplitude occurs. So come back over here, and again we're looking for an amplitude of 0.9975, and since that's pretty close to 1, I'm going to just use the zoom tool and zoom in on the line in this area. And then use the tracing tool to find the closest value to 0.9975. That's 0.96. And once you click on the line, you can use the arrows on your computer to scroll, which is what I'm doing right now, and I'm just looking for the closest value. And 0.9973 is about as close as I've been able to get. So you can see these values here. You have the amplitude is the y and the frequency is the x. So that tells us that the cutoff frequency is 2290. So we'll come back over here and write 2290. And then f oct, you're looking for the frequency that is 1 octave further into the stop band. And an octave is just doubling a frequency, so you're just going to double the value that you got for F cut, and you should get 4580 hertz. And then what you'll do is you'll find the amplitude at this frequency at F oct. So I'm going to zoom out a bit. And then use my little tracing tool. Okay, that's 4,000. I'm just gonna scroll. Okay. There's 4580, and the amplitude is 0.06325, so that is your A oct right there. And then you're going to find the attenuation rate of this system, and so that is basically the slope, which shows you how fast the system changes from passband to stop band. So that just kind of gives you this rate of, you can see the passing low frequencies and then the attenuation of the high frequencies. So yeah, he gives you the formula to find this in the directions, so I'll let you calculate that part on your own. Should be pretty straightforward, just using these values. And then you're going to kind of change your view of this graph, and you're going to look at it in dBSPL instead of pascals. So you'll switch that, and that's what your new graph looks like. And then you're going to look for dB cut, and that is just the dB value associated with your F cut frequency, with your cutoff. So you're going to come find 2290, which will be somewhere over here. And again, I'm just scrolling with the arrow keys on the computer. And so your output at 2290 is going to be 93.98 dB. So you'll come put that here under dB cut. And then you're going to do the same thing for this next one, but with your F oct frequency. So use the zoom tool to zoom back out a ways. And then looking for 4580. It's a lot of zooming and scrolling on this one. Okay, so your value at 4580 hertz is going to be 70.02. So you'll come put that over here. And then same thing, your attenuation rate, you have the formula for. So I'll let you guys calculate that part. A good way to check your work is that both of your attenuation rates should be the same value since you're looking at the same system. So the attenuation rate is just the slope at which it changes from passband to stopband, and that should be consistent between both views of the output, both in dBSPL and in pascals. And then you can see that there's two rows here. So for system A, let me zoom back out. For system A, it's a low pass system. You can see that because the low frequencies pass and the high frequencies are attenuated. And so you can see this slope or this change is only happening in one direction. From low to high, you're seeing attenuation. So for this answer sheet, you're only gonna have answers on the top row. You can leave the second one blank. But other systems are gonna be a little different. Like if you look at system X, I think, yeah, so you can see that you have two different slopes here because it's a band pass system. So it's letting certain frequencies up here pass, and then the rest are attenuated on either side of that maximum amplitude right here. So for that one, you're gonna go through and find the values in either direction.